Alright, so it was recording indeed. Fine, so sorry for the delay. Anyway, so our friend has asked a question, week 4 assignment, question number 5, right? So there is a question number 5 says this is the circuit for question 5, figure 2. So in question 5 we have, if Vi is equal to Vp sin omega naught t, find Vb while ensuring maximum possible Vp for which M1 remains in saturation and away from cutoff. So there is a hint which is use Q point plus incremental mode for analysis and ensuring a gain of minus 10. So you have to find out maximum possible Vp for which M1 remains in saturation and away from cutoff. No, sorry, you have to find Vb while ensuring maximum Vp. Okay, so what is the problem here? In the solution, you have a problem.
Yes, actually,
I'm unable to hear you.
yes, man can audible.
Yeah, you are audible now.
So, in like why they have considered like in one part they have considered current to be additive, then in another part they have considered like here. Uh, Once come down.
Okay.
So here, like it was considered in one case it was considered like both currents to be in the same direction, and in one other case it was taken like this should be greater than or equal to for cutoff. That I did not got actually.
Okay.
So why like that? I wanted to ask.
No, I cannot. Let me just ignore the solution here. I'll come to your approach. Fine. So the question was the question. See, in this question, basically, you have to find out what is the maximum VB, right? Such that your transistor M1 remains in saturation, and also you need to have maximum possible swing, right? That is the question, right?
Yes, sir.
You have to have maximum possible swing at the input, so that all the transistor remains in saturation, and for that you need to bias it. You have to bias VB in such, you have to bias this transistor M1 such that you get maximum possible VP. That's the question. While ensuring gain of minus 10. That's all you need to have. Correct? So,
Yes.
so now tell me, how do you, so basically there will be two limits, right, to maximum possible swing. What are the two limits? Okay, let me take such a digression, so I'll just cover it here. Yes, so you have this situation here, right? So this is the situation that you have. Now tell me, what are the limiting conditions where the swing will basically, what are the situations where this transistor can go out of saturation? Nikhil.
If VDD is less than VGS minus VT.
So VD, if VO, basically VD is here VO, right?
Yes,
VO, if
yes.
it is less than VGS minus VTH, then transistor goes into Linear region, right?
Linear. Linear, yes.
Yes. There is another condition also, right? Where the transistor can go out of saturation. What is that? If, so this is what? Case 1. Case 2 is if VGS is less than VTH, M1 goes into cutoff,
Cut
right?
off.
Correct, na?
Yes.
Yes. Also, other way to say this would be what? Say other way to say this would be, or basically your current, the current that is flowing through it, let's call it I small d, or ID will become less than equal to 0, right?
Yes.
Right. So when do you think these two conditions will happen? So basically, when do you think is upper condition going to affect, and where do you think the lower condition is going to affect? Basically both of these conditions you expect, right, in some situation, because if the signal, if the gate voltage here is swinging, right, so what is the net gate voltage here at this point? It is VB plus VP sine of omega naught t, right? Isn't it?
Yes.
Yes. So now this voltage here is going moving like this, right, in time.
It can be plus or minus.
Come again.
It can be plus or minus.
Yes, it can be plus or minus. So basically this is VB, right? This is VB, and this is VP plus VB, this node voltage. Huh? This is VB minus VP, correct?
Yes.
Yes. So tell me, uh, when do you think case 1 will happen, and when do you think case 2 will happen?
I think when VP plus VB, case 1 will happen.
Yeah, this upper, when it is swinging in the upper direction, right, then case 1 can happen, right? Correct.
Because VG increases.
Correct, because VG increases. So this is, both of these cases are case 1, right? And this guy, when do you think this guy will happen,
Negative actually.
right? So this will happen in the negative condition, right? This is case 2. So when you find out what is the maximum swing, you have to take both of these conditions. Swing means what? Maximum value of VP will be limited. So let's say you find out, okay, now let's take two cases, right? So you have to solve for both the cases. Case 1, you have to solve for case 1 first. Find out what is the maximum value of VP, okay, for which case 1 is not violated. Okay, you getting my point?
Like maximum value of VP for which it is not violated.
Yeah, so basically VD should be above, greater than VGS minus VTS, right? That should happen for case 1. I mean, for transistor to remain in saturation, VD should be greater than VGS minus VTS. That should happen. Okay? And from there you will get a maximum value of VP, isn't it?
Yes.
Yes. So the next condition, next case will be the other one, other way, where you have to find out what is the maximum value of VP, so that this VGS is never less than VTH. So a better way to represent this would be small VG as, okay, I mean V small g, okay. So in both of these conditions you will get a maximum value of VP. You have to take the smaller of these two. So the current equation which you are seeing there is a opposite sign, right? That happens because in one case you have to consider this, when the signal is moving in the, when the current is, sorry, when the signal is moving in the positive direction, okay. So when the signal is moving in the positive direction, this one, what do you think will be the direction of current here? This way, the direction of current, what will be the direction of current? What is ID?
It will be downward.
It will be downward only, right? Both the small signal as well as the large signal, right? There will be a bias current ID plus there will be a small incremental current, right? But both of these will be downwards only, correct? In the second case, when the signal is moving in this direction, in the negative excursion basically, what will happen in that condition? Bias current will be still downwards only, right? What will happen with the incremental current? What do you think should happen to the incremental current here, Nikhil?
It will flow downward because you're reducing the voltage, right?
Okay, so I have reduced the voltage. Okay, so tell me something. Uh, so net total current will flow downwards, there is no doubt there. Okay, so I am asking what will happen. So this ID that is flowing here is the net total current, okay? But this ID is a resultant of this one, right? Okay, so tell me something. I want to know what will happen. What will happen when your signal, when your input signal that is applied at the gate is moving in this direction, in the lower side? What will happen to both the signal, both the currents, capital I and small I? Direction basically I want to ask. What is the direction of both the currents? Okay, tell me something.
Small I will be opposite to
Yes,
big
yes, yes,
quiescent
yes, 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 exactly.
because it is changing as it is getting negative. Voltage is getting negative.
Yes, so basically this current, capital current, is always in the center because this is a bias current, right? Bias current is because of the DC, it is always flowing downwards, no doubt there. But this current, small ID, is going to flow upwards. Why? Because
The, the voltage is changing.
yes,
It is going to negative.
yeah, the
The
voltage
VP
is getting negative, right? And because of which the current ID is going to flow upwards, small ID, right? And now tell me, because of this, what is going to happen to this guy, a capital I small d, net total resultant? This is going to what? Decrease or increase?
Decrease.
Decrease, yes. This is going to decrease, which also makes sense, right? You see here at this point, mm, when the signal is in this domain, at this place, okay, when the signal is here, which means what is a net total voltage at this point? Is it increasing or decreasing here? Net voltage.
Decreasing.
Yes, net voltage is decreasing here, right? And you know that the current that is going to flow through this guy, the current that is going to flow through this guy, sorry, that color is not good. Yeah, the current that is going to flow through the transistor M1 is a function of VGS minus VTH, right? Is a function of the gate to source voltage. How much is the gate to source voltage? On that it depends, right? So if the gate to source voltage decreases when the signal is swinging, which means that the total current here should also decrease, right? Which is what we are seeing here. Is that point clear? Is that point clear, Nikhil?
Yes, sir.
Now tell me, if that point is clear, then yeah, then tell me, because of this, what do you think will be the, if you want to incorporate this in the equations, then basically what will happen? ID minus ID, right? So this was in this manner. So if you want to also write it in the, so this will become in this fashion, right? the current, since the sign is because the swing direction is opposite for this current, so you have to interpret a negative sign, right, for this current id, isn't it? So when you try to analyze both the situations, for the transistor to remain in linear region and for the transistor to remain out of linear region and for the transistor to remain out of cutoff, you have to take opposite signs for current. Do you understand that now, Nikhil?
Yes, ma'am. I was asking about this one. Like in one situation, it was considered both as like what do you call actual current plus incremental, and I didn't understand like why in one situation it was considered like actual current minus incremental. Yes.
Yeah. Fine. So let me now start with this week's content. Fine.
One more point. They have said like they have rectified that like
Nikhil,
will
I
be
cannot hear you properly.
avoided.
I'm not able to hear you properly.
Now is it audible?
Yeah, it is slightly better.
Is it audible now?
Yeah, it is slightly better. Yes.
Okay. As you have said, like yeah, the got right reply for that question. Will they award the mark for it again, or else?
Still, you are not audible to me.
Hello.
Yes.
I have raised some like there is some key mistake, right?
Yeah, you told last time. Yes, I remember.
Like, yes, I have got that reply back in that discussion forum. So, will that mark be awarded or like it will not?
So, what was the answer to that? I mean, reply was what? Did you get a reply
For
to
one
that?
question, yes, like they have said it is wrong for one question. So, in week one, that's all.
Yeah, so you should get. In that case, I think you should get. So, have you not received grace marks for that?
No, no, like the question was not rectified in the key. In the key.
So, what is the problem? I mean, grace marks. Do you not do you require grace marks, or do you like? What is the final this thing requirement from your side?
It would be good if we could like who are at, like given that right will get some.
So, what is the situation right now? Is there no change after your comment there?
Yes, they have replied it, but they haven't awarded marks yet. That's it.
Is the question? I mean, the other possibility is that the question itself is uh, understood as invalid. So, has that happened?
No, no, no.
Okay, so I'll confirm. Okay, I'll see what happens. So this is week three, right? Week three or week four? Week three, right?
That was week one.
Oh, week one. Okay. Okay, I'll see. I'll see what I can do.
Okay. Thank you.
Anyway,
Sir, there
yes.
is a doubt regarding previous one, sir, which you explained now.
Okay, this one.
Yes, yes, sir.
Yes.
Sir, in the first point you have written VD less than V subscript small gs. Why
Yes.
you have changed? Initially you have written it as a capital Gs only.
Yeah, yeah.
So
Is that it's a convention, right? I think the instructor is following a different convention, but I follow
yes,
this
yes, yes,
convention.
yes, yes. He is following that small V capital Gs.
Right. So I follow this
Yeah.
convention. I follow this
Okay.
convention.
Okay.
Okay. It's
Okay.
just a
Okay.
naming convention. It doesn't matter anyway. As long as you
Okay.
understand.
Concept is important. Okay.
And
Okay.
man, the key is actually updated. I've checked it now.
Okay. So which means that
Thank-
you will get the marks, right?
Yes, yes, yes. This key is updated. I've checked it.
Fine. Fine. Thank you.
Thank you.
Oh, not this one. Yeah. So so today we'll be discussing the content that was covered in week five, right? So what all things were covered in week five? It's a summary. Here is a summary for all those things. So we learned about how to find out the total current and voltage when you have a non-linear network. Particularly, we saw the case of a MOSFET, isn't it? We saw how to deal with MOSFETs when we have, when we give the signal swings to it. How does the current and voltage change dynamically, right, over time? Now we also learned about swing limits, how to find out swing limits, and we saw a particular case of MOSFET being used as an amplifier. That particular contraption of amplifier was a common source amplifier. Okay, so I'll tell you more about this. Do you guys understand what is a common source amplifier and why is it called a common source amplifier?
Between input and output, that is the common terminal.
Yes, correct, exactly, yes. So you understand. Good. So we saw a common source amplifier and then we found out how to deal with a common source amplifier, how the signal is amplified in a common source amplifier. We further moved ahead and saw the swing is uh, how the swing is getting limited in a common source amplifier. You cannot apply any voltage that you want, any voltage that you want, and sorry, let me rephrase that. You cannot apply any swing that you want, and you expect, you should not expect to get amplification. Amplification will be limited ultimately by the swing limits that you have in your amplifier. Okay, so all those things we saw. Now we also saw how to what happens uh, in the graph. So this was a simple representation only, graphical representation of signal swing. That's, I think you understood all those things. Yeah, the most important takeaway from this week was use of capacitor. Okay, use of capacitor to bias, basically to replace a floating battery, and how to find out what value of capacitor you should use. And then again, you also wanted to replace two voltage sources with just one voltage source. So all those things you saw. So do you guys have any doubt in this, content wise? Did you find any difficulty in understanding this? Yes, Saki, you have a doubt, you can ask me.
Yeah, so I have a basically question not related, actually related to the below points.
Mm-hmm.
So my question is, what is the difference between small signal analysis and incremental circuit
There is
analysis?
no difference, they are the same thing.
Oh, both are same, right?
Yes.
Okay. Yeah, okay, okay. Thank you.
Yes, yes. So I hope there is no doubt in the content that was covered.
Sir, can you
Mayank,
please,
Yeah, one
uh,
by one you can ask. So go ahead.
sir, use of capacitor to replace a floating battery, that I understood up to some extent.
Uh,
That the current will be going into the battery because battery is similar to a short circuit. That way, that I understood. That what I understood.
okay.
Uh, uh, is that okay or anything else? It is.
No, no, it's fine. I mean, okay. I will just anyway. I'll just for sake of clarity, I'll just again say something about it. So the thing is that, but before that, Nikhil, you were also asking something.
yes, like when, see, for some problems, when we need to consider that only what you call uh, like only current and when incremental, like when combination of both. That one I wanted to ask actually.
Oh, okay. See,
Like,
the thing is that MOSFET doesn't know what is incremental and what is bias, right? MOSFET always works on the net total voltage that it sees at its gate, isn't it? So the correct way, the most correct way, if I would say, the most correct way would be to find out the net voltage, okay, at all the points, at all the nodes, okay, and use the use the equation that you have, current and voltage equation that you know, okay. That is the most correct way. However, that is not always required, because in most of the cases the signal is small. If the incremental signal is small, then you may not require to do all those things. You can simply use the bias. You can calculate the bias voltages and bias currents, okay, in the circuit with the DC information that you have, and then using the small signal analysis, you can simply find out the small signal. You can simply find out the small signal swings at the different nodes, and to find the total voltage and total currents at different places, you simply have to add both of these.
so if they ask like what is maximum then
When
minimum,
the condition is
then we need to.
maximum, yeah, let me come to that. When when someone asks you what is the maximum swing or questions like this, which means that it may be the case that incremental analysis may not hold true in that case. Okay, incremental analysis holds true only when your signal is very small compared to the bias. Okay, or rather the overdrive. I think you remember this, right? The applied signal at the gate, the small signal at the gate, should be much smaller compared to the overdrive, isn't it? So if that condition doesn't hold true when you're trying to find out the maximum voltage swings at different places, that condition may be violated. So in that condition, you will not be able to use that small signal to large signal. You will have to go with the conventional thing, that is find out the net voltage at every node and then use voltage to current equation that you have for MOSFET. Getting my point?
Yes, sir. Yes, yes.
Good. So now coming to the yeah. So use of capacitor to replace a floating battery. Yes, that was the thing I want to discuss. So so let me take the example of again the same common source amplifier. So what we were doing earlier was this thing, right? We apply a small signal here. Okay. This is the common source amplifier, is it right? So we saw that VB, this voltage source here, is not available in this manner because we do not have access to both the terminals of a voltage source. And even if we do, it's not because in this condition we need dedicated voltage for each and every amplifier that we make. That is simply not going to happen. Okay, so this is not a good idea. This is not a good idea. So we wanted somehow to replace this battery, isn't it? Somehow we have to replace this battery to make and replace it with something else which will do the job. That was our requirement. Hold on a second. Okay. So in this situation, we want to replace the battery with something. Now, let us know. Let us try to understand what do we know about a battery. What is an ideal battery here, and why is this battery required? So with this battery, what is going to happen? What is going to be the signal or exact net voltage that we see at this node? This is VG, right? So what is going to be VG?
VB plus VP sin omega t.
VB plus VP sine of omega naught t. Good. So this is the VG that we know. This is going to be the net total voltage VG. Okay, good. Now for a voltage source, what is an ideal voltage source? What is an ideal voltage source? Doesn't matter. So what the ideal voltage source VI characteristic is how? What does it look like?
Linear.
So let's call it I. This is B, or rather, let's call it V. This is I. So it doesn't matter. No. How is it linear? It is extremely non-linear, right? So this is the voltage source characteristic, isn't it?
Current will be constant.
Correct?
But no, voltage will be constant.
Yeah. So it doesn't matter how much current flows through this voltage source. Okay. Doesn't matter how much voltage flows through this voltage source. It will always doesn't matter how much current flows through through this voltage source, it will always maintain a constant voltage of VB across it, right? That is an ideal voltage source. In other words, what does it mean? What do I mean when I say any amount of current can flow through it without affecting the voltage? It means what? Current is what?
Yes.
Flow of charges, right? Current is the flow of charges. So doesn't matter how much charge I take out or push inside it, its net level will never change. It's like a giant sea. Okay, it's a giant sea of charges where the sea level will never change, even if you put some dump some water into it, or even if you take a bucket of water out of it. It doesn't matter. The sea level is always going to remain the same, isn't it? So it's a giant sea of it's a vast sea of charges, isn't it? That's what a voltage source is. Is that point clear?
Yes, sir.
Yes, sir.
Good. So all we want, if we want to replace this voltage source with something, we want to mimic this giant sea, right? In some manner. We want to mimic this giant sea of charges in some manner. Now we have to look for this giant sea of charges somewhere else. We cannot use a voltage source. So we know something about a capacitor, right? What do we know something about the capacitor? What do you know about the capacitor? A capacitor, if it is a very large capacitor, okay? If it is a very large capacitor, we know that Q. So this is a capacitor, okay? Now, if the voltage across a capacitor is V and the charge across it is Q, so what do you think? What is the relationship between all these three parameters? It is V is equal to, or rather,
Q is equal to CV.
equal to C times V, right? This is something which we know. Or if we differentiate it with respect to time, we want to find out if voltage changes by delta, if the voltage changes slightly, what is the effect on the total charge, right? That is what we want to see. So if we differentiate it with respect to voltage only, so dq upon dv is equal to how much? C, right?
Yes.
What does it when I differentiated it, what does it mean to what am I trying to understand from this expression? It what does it say? This means that what is, or rather, let me write it in terms of delta q only. What does this mean? I am trying to look at this expression, and when I write this expression, I am trying to understand if I change my voltage by some delta V. Okay, if there is a small change in the voltage by delta V, what is going to be the change in the charge across it? Or if I write it the other way, delta V is equal to delta Q upon C. Correct? This is also true.
Sir.
Correct? Now tell me something. This expression, what is the physical significance of this expression? What am I trying to understand from this? I'm trying to understand that if the charge that is stored on the capacitor, if it changes by delta Q, okay, earlier the charge was Q, okay, if there is small change in the charge by delta Q, how much is the voltage going to change across the capacitor, right? This is what it signifies. Okay, now as you can clearly see, this voltage, the change in voltage because of the change in charge is inversely proportional to capacitor, isn't it? And from here we can get an idea what was the requirement from our ideal voltage source. We wanted to the voltage to be independent of the amount of charge that is taken out of it, right? Or the voltage across the voltage source should be independent of the delta Q, right? The charge that is changing across it. And we see that a capacitor provides that opportunity to us. We just have to ensure that the capacitor should be large enough, right? If the capacitor is infinity ideally, then our delta V will be 0 irrespective of the amount of charge that I take out of it, isn't it? Is that point clear? Which means that if the capacitor is infinite and once it is charged to a certain voltage, okay, then no matter how much charge I put on it, how much extra charge I put on it, or how much extra charge I take out of it, it will always remain fixed at the same voltage. Is that point clear?
Yes, sir.
So this is what this is how we are going to replace a battery with a capacitor. We'll just put a capacitor there and charge it to some voltage. That voltage will be the battery voltage. Once it is charged, it then behaves very much like a idle voltage source. Okay, fine. So can I now move ahead with the problems, or do you have any other doubt in the content?
Yes, ma'am.
Fine. So today I have only one question, but this question will be quite long. This is very this is the same question as the one that was given in the assignment. The slight twist here and there. So here we have this contraption. Okay, this is a common source amplifier only, and we remember, right, that we wanted to replace two voltage sources with one voltage source, right? So that is why we use this resistor divider here, correct? This will generate the required voltage that is that we need here, required DC voltage, and that DC voltage is then charged that this capacitor C1 is charged with the DC voltage VG, okay, and then we also apply this small signal or small sinusoidal signal, and at the output side also we have a capacitor. So if can anyone please unmute themselves and just try to explain me why this capacitor at the output side was required, C2? Why did we need this capacitor, C2?
So the current entire like if it is not there, then current will go entire will decrease.
Yes,
It will flow
exactly.
into RL.
So if this capacitor is not there, the current that is coming here, right, is going to flow parts through it and parts through this, right? This is simply going to load your voltage, output voltage. The correct term is loading, right? It is going to load your MOSFET, isn't it? So this is not a good idea. So we and also see, this could have been possible if we knew what is the value of this load resistance RL. As it turns out, load resistance RL is not generally in our control. When we design something, we design only this part. Okay, we design only this part. The RL and RS are not in our control. They will be when you sell this item in the market, RL and RS will be in the customer's choice. It can be anything between a range.
Like the voltage source they have an internal resistance. That is RS, right?
Correct. This RS is generally the voltage, the resistance which comes with the voltage source. Yes, correct. So these two things are not in our control. RS and RL are not in our control. These are as per the customer's choice, and this can vary in between a range. So that is why we have to design such that our amplifier's performance is not impacted by the values of RL and RS. Okay. Now I have given some values here. VDD is equal to 8 volts, RS is equal to 1 kilo ohm, RD is equal to 2.5 kilo ohm, R2 R1 is given here, RL also 10 kilo ohm. Fine. So tell me now, the first question is find the small signal gain from Vi to V out, assuming C1 is equal to infinity and C2 also tends to infinity. So basically, for now, you just consider both these capacitors are infinity, which means what? Infinite capacitor means what?
It's like a battery. Like a battery.
Correct. Exactly. They are like battery, right? So it's the same situation as the normal case that you solve. Right? So battery, in this incremental analysis, what do we do to a DC battery? What do we do to that? We short it, right?
Shorted.
Yes, good. So before doing that, but first we need to, for the small signal gain, we need the small signal parameters, right? Operating parameters we need, operating points we need, operating point information. So for that we need to find out what is the current, what is the GM, right? We need to find that out. So tell me what will be the GM here. First tell me what will be the voltages here. So
Mayank, so as I've said, right, if C2 is present, then the entire
there is a lot of noise, lot of background noise in your area. So it would be a great help if you can just come out of that place, or because I cannot hear you in that all that background noise. Either you speak high or you take a different place. If you have a doubt, you can.
Mayank, I just have a request.
Huh.
Could you please provide some numericals for every assignments separately for our practice and all?
This is the one that I. This is the one that is for practice, right? Here we
Yeah,
solve it
but
together.
if you have
No, I have a lot of
other,
question. I have a lot of
yeah,
question. It's
so
just that.
please.
It's just that you have enough for understanding, because this things which I solve here uh, will be a great help for you. If you try to understand it here itself, the things that I'm trying to explain, you will be able to solve anything. Okay, there are a lot of places where you can solve a lot of questions. That solving a lot of questions doesn't help if you do not understand what you're doing. So question, even if you solve only 2-3 questions but you understand what you're doing, then you will be golden.
No, what you are describing, it's very helpful. It's really helpful. But after that, if after understanding that, we have to do practice some practices, right? So for that, we need a little. If you provide some other
You can
examples.
okay, so there are a lot of sources. Okay, there is a book by Behzad Razavi. Okay, analog CMOS integrated circuits, I think that is the name, by Behzad Razavi. So that book you can go through. There will be a lot of questions there. Okay.
Okay, thank you.
Yeah. Yes, Nikhil. See, if C2 is there, then no current will flow through RL. That is true. No current will flow through RL. This is true.
it will block DC current,
Yeah, yeah,
right?
it will block DC current. So what will be the voltage at this point? DC voltage. So what will be VO DC? What will it be?
VDD minus IDR.
Is that it? Because you said that no current is going to flow through this, right? No DC current is going to flow through this guide, isn't it? So how will the DC voltage at this point will be? I mean, if there is no current flowing through this, then what is going to be the DC voltage here? VDD minus IDR. How it can be? I'm asking what is the DC voltage at VO? This guy. What is the DC voltage here?
Is it a zero, sir?
It is zero.
Because
It can nothing. It can be nothing else. It has to be zero, right? If the current flowing through a resistor is zero, then the voltage across it is also zero, right? It's not IDRD. IDRD, VDD minus IDRD is the voltage here. But between this and this point, you have a capacitor, and the capacitor is something which acts as an ideal battery here, isn't it? An ideal battery can have a DC voltage across it, isn't it? There will be some DC voltage at this point, and DC voltage at this point will be zero. The voltage that drops across this ideal battery is the voltage. I mean, there will be a voltage drop across this ideal battery, isn't it? That is what it is. Okay. So we have some parameters here. So also copy this. Okay. So V0 DC is DC, VO DC is DC. Fine. What else? What is VG? What is VG? VDD into R1 upon, sorry, to R2 upon R1 plus R2, right?
Yes, sir.
Right now? Fine. So what will this be?
Three.
VDD into, you simply take the ratio, I mean divide both up and down with R1, right? So this becomes 8 into 3 upon 5 1 plus 3 upon 5 becomes 8 into 3 upon 8, right? 3 volts, correct. So VG is 3 volts, no problems there. Okay, now tell me, now tell me what is the current that is going to flow through this transistor. What is ID? Mu n, assuming that the transistor is in saturation, right? That is how we do it first. We assume that the transistor is in saturation, and then we solve for the current. Then we check whether that assumption is actually true or not. If it is true, then it is good. Otherwise, we have to then basically, which means that transistor is not in saturation, and hence it will be in linear region. So first we have to assume it is in saturation. So okay, so how much is this? Mu n Cox W by L is 1 milliampere per volt square. This is 1 by 2 into 1 milli, which is 10 to the power minus 3. Then VGS minus VTH is how much? 2 to the square, right? 2 square, which is 4. So 4 by 2 is 2 milliamperes, correct? So what will be voltage VD? What will be voltage VD? This will be 8 minus ID 2 milli
idea RT.
RD, right? So RD is 2.5 kilo. So this is 8 minus 2.5 into 2 is 5, again 3 volts, right? So VD is 3 volts. So tell me, is our initial assumption correct or not? VG was 3 volts.
Yes, it's correct. It's
It's
satisfying.
correct, right?
Yes, sir.
So transistor is in saturation. Now, what will be the GM of this? Now we have to find out the small signal parameters, right? For finding the gain. So what will be the GM? You can use any formula that you want, so I will use this.
Yeah, why 2 millisiemen?
Yes, so this 1 into VGS minus VTH is 2. This is 2 millisiemen. Huh, good. Now, what will be the small signal diagram of this incremental analysis? For that, we need a small signal picture, right? So, how will this look? Or rather, tell me now that you are very familiar with it, what will be the small signal gain from VI to Vout? So, how small signal equivalent? Let us draw. In the small signal, all the DC voltage sources are shorted, right? So this VD, this capacitor, all of them will be shorted, correct? So let's do that first. So this is ground, then we have this R1, this R2, we have this MOSFET here, grounded, another ground here, RD, then we have this RS, VI, it's also shorted, so RL, this is V out, VO rather. Yes, this is the small signal first step, right? From here only you can you tell me what will be the gain from VI to V out, VI to VO?
GM into RD parallel RL.
Minus, don't forget the minus sign, okay?
Yes, sir.
Minus GM times RD parallel RL. Anything else? Okay, first tell me what will be the signal that reaches here, VG? What will be VG? What will be VG? Hmm?
If we take like that uh, parallel combination to be 10 to infinity, then it will be VI.
No, no, don't tend it to infinity. I have not asked you to tend it to infinity, right? There is no information like that. Tell me exactly what will it be.
VI
Into
minus
into
R1 parallel R2
R1 divided by
by RS plus R1 parallel
RS plus R1 parallel R2. Okay, good. So VG we know. So now tell me what is VO upon VG, or rather what is VO in terms of VG? It is minus GM times RD parallel RL, right? Times VG, right? Is this right?
Yes, sir.
Yes,
So that
yes.
what is VO upon VI? It is also written as VO upon VG into
VG.
VG upon VI. Exactly right. So now we have both these, right? VG upon VI we have, VO upon VGA we have. So just multiply both of these, right? So this will be minus GM times RD parallel RL into R1 parallel R2 divided by RS plus R1 parallel R2. Isn't it? This is the gain. Correct? Okay. Let's not put the numbers here right now. Let me ask you something like this. Let me ask you this. So if I want this is some gain, right? This is some gain value. So
Mind once again.
yeah.
Reiterate this two steps.
Yes, Nikhil, you have a doubt?
Once again, explain this.
Oh, once again explain this. Okay. Yeah. So this is this you understood, right?
Like V not by VI, that last step.
Oh, this point.
Yes.
Oh, okay, okay. So what is this point you understood, right? The first one.
Yes, first, second I understood, but
So basically I simply took the so from here, what is VG over VI? Right? From here, what is V over VG? This is also right. Correct?
yes, ma'am.
So I have simply multiplied these two. This I have also written here, right? First one is the
Yes, yes,
got it. Is this clear now?
yes, yes. So, like, when those two tend to infinity, then there will be no problem. Directly we can take.
So that is what
If
I'm
there's
coming
a
to.
risk.
I'm coming to that.
Okay.
So we have a gain
Yes.
here. Okay. So what is the magnitude of this gain? Because we see there is a negative sign, right? So we are not particularly bothered about the negative sign as this at this moment. All we are interested in is the magnitude of this gain. So what is the magnitude of this gain? GM times RD parallel RL into R1 parallel R2 divided by RS plus R1 parallel R2. Okay. So now if I want to maximize this gain V over Vi, what should I do with R1 parallel R2? What should I do with this? When will the gain V over Vi be maximum?
If R1 parallel R2 is very high, then
Yes,
complete on.
exactly, right? Because the maximum value that this guy can take, what is the maximum value that this guy can take is how much? 1, right? Isn't it?
Sir.
The maximum value that it will have, this can at max be equal to 1, right? It cannot be greater than 1. Is that point clear? Is this point clear?
Yes.
Yes, sir.
Okay, good.
Yes,
If
ma'am.
this point is clear, then so tell me what will be the when will that maximum be achieved? When will we achieve this maximum? So R1 parallel R2 upon Rs plus R1 parallel R2 is always less than equal to 1, right? So 1 is achieved when,
R1 parallel R2 is infinity.
yes, correct. So for maximum gain, what do you want? R1 parallel R2 to be infinity, isn't it? But as you know that infinity is something which mathematicians have made, right? It is not something which we see in actual life. Mathematicians, it's a mathematician's construct, simple. Infinity is not something which is observed in nature. So if we are not allowed to use a infinite resistance, what is the next best thing which we can use so that the gain is very close to 1? So there will come a point when basically if the R1 R2 is very small, then you will have a very small gain, right? But as you keep increasing R1 parallel R2, your gain will start improving. But there will come a point after which even for 10 times increase in R1 parallel R2, you will get a very small increase in gain. So the if you want to draw the gain with respect to R1 parallel R2, it will look something of this kind. So if this is gain, which is mod of VO over VI with respect to R1 parallel R2, it will look something of this kind. Okay, so tell me something. Basically, so as long as basically you want to enter in this region, right? You want to enter in this region, and even and once you enter this region, even if you keep on increasing R1 parallel R2, you will not get any significant increase in gain, right? So tell me, what is that? What is this region? Where does this region start? I mean, how do you know how much is this value of R1 parallel R2 for which you will get enough gain, and after which you will not, even if you increase R1 parallel R2, you will not see much difference.
R1 parallel R2 is greater than Rs.
Yes, good. So this is basically a place where R1 parallel R2 becomes much greater than Rs. Once this is true, once if it is much greater than Rs, after that it will not even matter. Okay, after that it will not matter even if you keep increasing R1 by R2, it will not matter because the gain is almost saturated after that. So if you are a designer and you want to because higher value of resistance if you want to buy in market, you probably have to pay more, right? So you want to spend less money, so for that you want to have a smaller value of R1 per R2. So how small can you go? As a designer, as an engineer, you will want to make R1 per R2 at least 10 or 20 or 100 times more than Rs, right? If you do that, you are good. So this is something which I wanted to explain to you. So this is clear, right? So what is the maximum gain? Maximum gain is Gm into Rd parallel RL. And what is this equal to? Gm is equal to 2 millisiemens, right? And Rd is equal to how much? Rd is equal to
Mayank,
2.5 and RL is equal to 10 kilo ohms, right? So Gm times 2.5 kilo parallel 10 kilo ohms. Now other question that I want to ask you is this gain is still Gm times Rd parallel RL, right? This gain is
Mayank,
yes.
I have one question. Like gain means we need to take that negative also, right?
Yeah, you want to take negative, exactly, but I am right now I'm talking about magnitude of gain. Okay, I'm interested in magnitude.
So, like in general, if they say gain means along with that sign we need to
Yes,
consider,
you
right?
have to, yes.
Okay, thank you. That was the
Yeah.
question. Doubt I was having.
Now
Thank
the
you.
GM, this gain magnitude to be precise, is GM times RD parallel RL. If someone, now as I told you, RL is not in our control, right? It is not in our control. It is in the customer's control. All we are going to design is the block that is inside this box. We are only going to do this much. After that, RL is something which the user will choose according to his or her own convenience. Okay. So, if I want to make sure that this RL is not going to affect my gain a lot, what should I do with this RD? So whenever I try to sell something, I'll have to tell what is the gain of my amplifier. Okay, and once I tell that the amplifier's gain is this much, and if suddenly user puts some value of RL and the gain suddenly drops, it will be very bad thing, right? That I do not want to happen. So tell me, how will I maximize the gain still with respect to R? I mean, how do I make this gain independent of RL? How do I make the gain independent of RL? Because RL is something which is not in our control. So how do I make this gain independent of RL?
RD should be as small as possible.
So RD I will make 0. Then will I get any
No,
gain?
no, 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 not that. You have to maintain the relation amplifier in the saturation region, right?
Uh,
So
Also
first,
you also have to get a good gain also, right?
yes.
Yeah. So then go ahead.
So first maintain the saturation level, and then I think just a multiplication factor.
See, you were on the right track. Just missed a small point. RD should be kept very small with respect to RL. Okay.
Okay, thanks.
Yeah. So RD has to be very small with respect to RL. So when you start designing, if for gain to be independent or rather a good word will be insensitive. To RL, RD should be much smaller than RL, right? If we do that, then RD parallel RL will become RD itself, right? That is the whole point. So in that situation, your VO over VI, this becomes GM times RD, isn't it? Now,
Man, I have one more question. When you make RT, like I got it, like when RT is very less than RL, that becomes GM times RT. But aren't we decreasing the gain also here?
yeah, I'm coming to that point exactly. That is a very good point. So the thing is that when I say that RD should be much smaller than RL, right? That is something which we have to make sure. Now, with this, our requirement that the gain is insensitive to the variation in RL is satisfied, right? That is one of our requirement. However, while achieving that, we have also sacrificed our gain, correct? But you see,
Yes,
the
yes.
gain can be compensated, right, by increasing the value of GM, isn't it? When you start designing, you know that RD has to be much smaller than RL, right? So you can pre-distort and increase the value of GM itself to achieve this required gain, isn't it? All you want, the gain is equal to what? GM times RD. If RD reduces, GM can be increased. Is that clear, Nikhil?
Yes, man. Yes,
Yeah.
it's clear.
Now the other point that I wanted to impress upon here is that earlier I was saying that RL, it should be completely independent of RL, right? The gain should be completely independent of RL. But you see that while taking this assumption also, I have to assume that RD is much smaller than RL, right? But this will not happen for any value of RL. This assumption will not hold true for any value of RL, right? Let's say RD is, I have taken RD equal to 1 kilo ohms. So this assumption will hold true as long as RL is much greater than 1 kilo ohms, right? Let's say I give it to a customer and the customer simply puts a RL equal to 1 ohm. Then this will completely break, right? This assumption.
Yes.
Yes. So the catch here is that whenever you buy an amplifier from somewhere, they will always give you a number, uh, a constraint on RL that you can use. Okay, the uh, the the company that manufactures an amplifier will always give a constraint on the RL value. They will say that the gain is valid only for RL greater than a certain value, or they will give you a range. Okay, that RL should be used from this between this and this value. Okay, if you go lower than that, you will simply start loading the amplifier itself. Okay,
I got it.
yeah, I hope this is clear. Yeah, so the point that I want to explain was this only. So the ideal requirement for an amplifier is that your gain should be insensitive to the value of load resistance that you have, that is applied externally. Also, to maximize the gain, your the resistor divider that you place here should should not lead to any loading, right? Should become infinite, so that there is no voltage drop at this point. There is no voltage drop across this. Okay, okay, good. So once this is clear, uh, so these 2 points already done. Now find the constraint on C1 and C2 if F0 is equal to 50 MHz such that maximum signal amplification is obtained. Now, in the earlier question, I assumed that C1 and C2 are infinity, right? That is, they become ideal battery. However, in this part, that is not true anymore. Take this. Okay. Now, in this case here, the two capacitors C1 and C2 are not infinity anymore. Okay, and you want to find out. So this is basically problem number 3. Solution. This is 1. Okay. This part was second. Or rather, this is 1 only, and 1 and 2 are mixed together. So this is the third one. So here the capacitors C1 and C2 are not infinity. Okay, so in that case, what will be the small signal gain if C1 and C2 are not infinity anymore? Can we short them in the small signal picture?
No.
Yes. So how will the small signal picture look like? Small signal equivalent. What all things will be gone in the small signal equivalent? Tell me. This VD, right? This VDD. It will be shorted to ground. Correct?
Yes.
But that's it, right? Nothing else. So the small signal equivalent here will look something of this kind. So this VD is again pulled to ground. No problem there. Then you have RD like this. Then you have ground again here. You have a capacitor C2. RL. Yes. So tell me what will be the small signal gain from Vi to Vo?
And we need to consider the voltage drop across C1 and C2 also.
There will be a voltage drop across C1 and C2 also, right? In the small signal sense. Correct?
Yes, yes.
So let's call this as Vc1 and let's call this as Vc2. So tell me, when will the gain be maximum? When the gain will be maximum, what happens to Vc1 and Vc2?
They acts like short.
Short.
Correct. So then Vc1 equal to Vc2 equal to 0, right? Am I correct?
Yes.
Yes. Uh, but again, for that to happen, what is the requirement? C1 and C2 have to become infinity, right?
Yes.
And that is something again which only looks good in books, right? It is something which is not practically possible. Then tell me what is practically possible. Again, going by the same analogy here, that
We
after
need to reduce the drop across capacitor.
basically the
Like
drop across the
minimize.
capacitor, when it becomes negligible
Should be
compared to other drops, right?
Yes.
Right. The drop across this capacitor, there will come a time when the drop across this capacitor becomes negligible, after which even if you increase the capacitor value, you will not gain much, right? So that point if you achieve, then you basically settle with that, right? You settle with that value capacitor and you say that the design is completed. So tell me, how do you find out that value of capacitor for which your drop will be drop across this capacitor is very small?
Thevenin's equivalent.
Yes, Thevenin's equivalent. Yes. So let's take different sides. Okay, let's take first the input side. And why am I doing this? Why am I first considering only the input side? It's because for the signal,
Biasing is important.
come again, Alok.
I'm saying biasing for the biasing only.
No, it's not biasing right now. I'm talking about the small signal picture. This is a small signal picture, right? But I'm
Okay.
taking first I'm looking at the input side here, and then I will look at the output side. Why am I doing that? You see, for if the gain is I want the gain to be
Like
maximum, right?
C1 is with respect to what, right? That's why.
Again, I'm not
Sorry,
able
I
to.
joined late, but I was thinking like that these C1, C2 generally we called as a coupling capacitor, right?
Yes, they are coupling capacitor. Yes.
So we generally ignore this when we are doing the some calculations only.
Correct. Okay, you ignore this generally, but when you ignore this, you ignore assuming certain things, right? You assume that this is so high that it doesn't matter. But when you
Yes,
start designing, you'll have to use some value, right? You cannot use
yes,
infinite value. That is not something
yes.
which
At
will.
certain frequency only the gain it will affect because it is a capacitor's
Uh,
value.
correct.
It will affect on certain frequency.
Correct. So it's a capacitor. It's a frequency dependent. A capacitor basically presents a frequency dependent impedance, right? So
Yes.
in certain frequency it will act as short, certain it will not. So why am I considering first this input side and not everything as a whole? It is because uh, we want the gain to be maximum, right? The gain from Vi to Vo is something which we want to maximize. Now the gain from Vi to Vo is basically what? It is the gain from Vi to this point and then from this to this point. Correct? So I'm breaking my gain into two parts. First I will maximize this gain from here to here, and then I will maximize gain from here to here. Okay? And this I am able to do because the information from here to here is passed only in one direction. Okay? And uh, basically this guy, how How do I explain this?
Actually, as per my view, as Vi will increase, it will affect the gate, and that gate will change
Yes.
certain current in the transistor.
Yes, yes.
According to that, we will get the
Yeah,
output,
so
right?
the same thing, exactly, yes. The thing is that I want to maximize the gain for that I want to maximize the signal transfer from Vi to this point to gate, right? If I am getting a large signal at gate because of this Vi, only then will I see a large signal at the output also, right? For maximum amplification, I want maximum signal from Vi to be received by the gate, isn't it? And for that only
Yes, Max.
I want to maximize the value of C1. Okay, now tell me, as Nikhil was saying, we have to find out Thevenin's equivalent. Okay, so if I only look at the gate side, how will the circuit look? So I have Vi, okay, I have Vi, then I have Rs, okay, then I have C1, then I have R1 parallel R2. Because both are grounded only, so I'll just put it here itself. R1 parallel R2, right?
Yes.
I
Yes.
want I want the signal drop across this VC1 to be equal to be tending to 0, right?
Hmm.
uh, so what is VC1 here? What will be the value of VC1?
Vi minus I times Rs minus I times R1 R2.
Correct. So you can also find it out by Thevenin's equivalent, isn't it? So this is actually Thevenin's equivalent only, you are saying. So it is Vi minus I times Rs correct. And what is I? What is I? Is Vi upon Rs plus R1 parallel R2 plus 1 over j omega C1, right?
Yes.
Correct now? So this
Yes.
becomes how much? What is VC1 in that case? Vi into
1 minus
1 minus
Rs plus R1 R2.
J omega C upon 1 plus J omega C Rs plus R.
so how much is this? It is 1 over j omega C1 divided by Rs plus R1 parallel R2 plus 1 over j omega C1, right? So you could have already you could have said this directly, right? Simply using the voltage division formula here. You want to find out VC1, right? Everything is in series. So what is voltage VC1? It is the impedance of C1, right? That is 1 over j omega C1 divided by everything in series. So Rs plus R1 parallel R2 plus 1 over j omega C1, isn't it? This you could have directly said. Anyway, so from here, what is the value of VC1? Vi into j omega C1, j omega C1 cancel each other, and you have we're left with j omega C1 times Rs plus R1 parallel R2 right? So what is the time constant? What is the order of this basically? This is a first order thing, right?
First order, yes,
One
yes,
pole.
first order.
It's a one pole system. So what is the time constant?
C1 into RS plus
C1 into RS
RS plus R1 parallel
R1
R2.
parallel R2, right? And this also you could have directly said time constant from looking directly at this point, because you see, how do you find out time constant for a first order circuit? You take the you take the capacitor and you simply open the capacitor, right? So basically this is the point. You open it the capacitor, you short the independent voltage source, and this is another resistance R1 parallel R2, this is RS, right? And then you find out what is the um, basically you want to
Equivalent
find out
resistance
what is
and
the
RTS,
Thevenin
resistance and
resistance,
Thevenin's
we were multiplying.
Thevenin's resistance.
right? You want to find out what is the Thevenin resistance. So between these 2 points you want to find out what is the Thevenin resistance. So Thevenin resistance is, because these are in series, right? RS and R1 parallel R2 are in series, correct? That is why you see this here also. So the time constant here is C1 times RS plus R1 parallel R2. So tell me something, at what is the constraint on C1 such that uh, you your VC1 becomes almost negligible? Tell me.
No, I have a question here. The R you told that R equivalent, but R equivalent we generally find out and C equivalent we find out. Then we can
Yeah,
decide the
correct.
R time
Because
constant.
in this case you only have one capacitor, right?
Yes, so either we can do this R1 parallel because it is in the series, so we can do one side only RS and R1 parallel R2 one side and then capacitor. It will be same, I think.
Yeah, it will be same. I mean, whatever suits you.
Yes.
But anyway, so this is fine, right? Okay. So tell me, what is the constraint on C1 for VC1 to be almost zero? What do you want for C1 to be VC1 to be almost zero? What do you want? How will this look like?
Time constant will be less.
Basically, your VC1 should be is equal to this guy, right? So if you take the magnitude of it, what is the magnitude of VC1? This is the magnitude of Vi into magnitude of this guy, right? So what is the magnitude of this guy? Magnitude of 1 is 1. This is a complex number, right? So what is the magnitude of a complex number? Real part squared plus complex part squared. And then take the under root of everything. Take the square root of everything, right? This is the magnitude, isn't it?
Yes.
Yes. So now what do you want? You want this guy to be, so you want this guy VC1 to be very small, right?
This part should be high, right?
Come again.
This bottom part should be high, then only it
Yes,
will
yes.
go to
So
the.
you want VC1 to be very small, correct? You want VC1 to be very small. Yeah, so other thing is that how small do you want VC1 to be? I mean, there is always the thing, VC1 should be small compared to something, right? So what is that comparison? VC1 should be very small compared to what? It should be very small compared to the signal itself, okay? Or in other words, your VC1 upon Vi should be very small compared to 1. Okay, this is what you want. So here you have Vc1 upon Vi, right? So what is Vc1 upon Vi is equal to 1 upon root over 1 plus omega square. So 1 square is 1, right? So I simply replace it with 1 omega square C1 square Rs plus R1 parallel R2 the whole square. So I know I am going step by step at this because this is very important. Okay, if you understand this, you will not have difficulties later on. This will come again and again when in your life as analog circuit designers. Fine. So this you want it to be much smaller compared to 1. So what will it look like ultimately? So you take this denominator to the right hand side. So become 1 is much, or first let's just square both the sides. Okay, let's square both the sides. So squaring both the sides. Okay, this becomes how much? This becomes 1 should be much less than 1 plus omega square C1 square Rs plus R1 parallel R2 the whole square. So 1 and 1 cancel each other. I made a mistake somewhere, did I?
Sir, 1 much greater than 1 plus omega square in the whole equation.
Come again.
1 much greater than 1 plus omega square C1. We just changed the LHS and RHS, right?
I did something wrong somewhere.
No, sir. In the
No,
last
no,
equation, last.
it is correct only. It is not a wrong. It is.
Yeah, tell me what you are saying.
Uh, sir, you mentioned 1 much lesser than the whole equation you written, right?
Yeah. Yeah, I wrote it here. Vc1 over Vi
Yeah.
should be much smaller than
Sorry,
1.
sir. It's fine. It's fine. Sorry,
Okay.
sir. It's my mistake.
Yeah, fine. It's okay. So basically, you want this guy to be much less than 1 plus omega square C1 square Rs plus R1 parallel R2 the whole square. Okay. And this becomes this and this cancel each other. So what do you find out ultimately? Omega square C1 square Rs plus R1 parallel R2 square to be much greater than 0. Okay, there is a small problem here. It shouldn't happen like this. The ultimate result is not like this. Okay, there is a small problem here.
I think
Hmm.
this should be like omega square C1 square. That should be much greater than 1, I guess.
Yeah, correct. That is the condition. So tell me
Hmm.
what is the mistake that I made here.
See, if VC1 should tend to 0, the denominator should be greater, right? Like it should tend to like omega square
Yeah,
C1 square
that
should
is
be
true.
much greater than 1.
Correct. It is true. Tell me what is the mistake that I made here. What do you think is the mistake here? See, the mistake here is that I assume Vc1 Okay, this VC1 should be much smaller compared to VI, right? This is what I assume.
Yes, sir.
Yeah, this is not correct. See, the assumption should have been whatever voltage this VC1 is dropping, it should be much less compared to what? Ultimately, what are you interested in? This VC1 should have not been here, right? Ultimately, this should have been simply a short like this, right? Correct now?
Sir, VC1 should be 0.
Ultimate, that was the assumption, right, earlier. But here,
Yes.
this is your requirement. Ultimately, VC1 should be as small as possible, right? So how small should it be? That is the point, right? How small should it be? Hmm. So it should be very small compared to what? It should be very small compared to something, right? So what is the comparison factor that I should take here? I assumed earlier that VC1 should be much smaller
Sir,
compared
it's
to
not VI. It's not VI, but like entire voltage drop you need to take, I guess.
what entire voltage drop? Which voltage drop are you thinking?
VC1 must be very, very much less than
Hmm.
when compared to voltage drop across RS plus voltage drop across R1, R2 parallel.
Yes, basically it should be much less compared to the voltage drop that will happen because of the series connection of this RS plus R1 parallel R2. Okay, that should have been the condition. Getting my point? So exactly, yes, Nikhil, exactly, you are correct. So our constraint should have been, so this is Vs, okay, let's call it Vi, and this is Rs, this is your C, this is Rs R1 parallel R2. So ideal condition would have been what? Ideally this was Vi, Rs and R1 parallel R2, right? This was the ideal
Voltage
situation.
across R1 parallel R2 will going to affect the transistor, right?
Yeah, R1 parallel R2 is going to affect the also going to
No,
affect.
whatever the signal coming from VI and whatever it will create a voltage across the R1 parallel to R2, that is going to affect the transistor gate.
Yes, yes, true.
Hmm.
What I'm saying is, ultimately, uh, this was the situation, right? So, basically, this voltage, the condition should have been that VC1 should be such that VC1 should be much less compared to the voltage drop that happened because of this RS. See, what I'm trying to impress here upon is that due to RS also, there will be a voltage drop, right? Ultimately, what do you want? You want all the Vi to come across this point, right? At this point. But because of this RS, there will be some voltage drop, isn't it? Even in the condition where the capacitor is infinity, there also you will have some effect due to this resistance RS, right? At this point, you will have some value, some drop, right? Due to this RS, you will have some drop. So all I want from my capacitor, C, this capacitor C, is that the drop that that we have across the capacitor C is much less compared to the drop which we have across the resistor RS. Because even if after that even if the drop across the capacitor is very small, it doesn't matter, right? The signal is anyway going to be dropped because of this resistance RS. Are you understanding what I'm saying? Is this point clear?
Yes, and the drop across C should be less
Much less
than
compared to the drop across RS.
ours. Yes.
Okay, So this should happen our.
So
Huh.
RS as well as R1 parallel R2, right?
Why R1 parallel R2? If you take the drop across RS and the drop across R1 parallel R2, you will get the VI itself, right? Am I right? What is the drop across RS and R1 parallel R2 added to this?
What I'm saying is in like this one left side, right? Diagram circuit.
Left
So
side, yes.
uh, the drop at capacitor must be very very much less than the sum of voltages drops across RS as well as R1 parallel R2, or only RS we need to take.
Only RS, right? What? Why R1 parallel R2? R1 parallel R2 is something which you desire, right?
Okay.
As per my view, I think voltage across the RS plus this capacitor should be very very less than the R1 parallel to R2.
This is also true, yes, but that will pose a constraint on both R1 parallel R2 and everything. So what I'm saying,
Yes.
okay, so this is a good homework for you. See the I because of time constraint, I will not be able to finish it today. So anyway, this is a good homework for you. So because uh, we used to when we are conducting quizzes here, right, at IIT Kanpur. So this is a very famous question uh, that we give to students here, and we get all the three types of results that you are just saying right now. They take all the three conditions. That is, that this is the first condition, and the reason I wanted to do it in this way is because I wanted to explain to you the conditions. So this is the first thing that this is one of the most popular solutions that they do. Okay, where they simply take the constraint here like this, and then they come up with this particular condition. So this is something which is we cannot say it is entirely incorrect, but is not very correct also, right? The second constraint that they put is that the capacitor C1 such that the voltage drop across C1 is much less compared to voltage drop across RS. This is the second kind of constraint. The third one is that Nikhil was just saying that the voltage drop across the capacitor C is much less compared to the voltage drop across RS and R1 parallel R2. Okay, so this is another constraint, and what Alok you were saying was exactly the same thing as Nikhil. Okay, so I would like you to find the constraints in all the three. Sorry, so this one is already done by me. I want you to solve using the two constraints that we didn't discuss. The one where VC is much less than compared to VRS. Okay, and the second one VC is much less compared to VRS plus V R1 parallel R2. So where do you think is the? I mean, I would like you to solve using both of these, and tell me which will be the correct one. Just a hint. This will be the most correct one. Okay, as Nikhil pointed out. So this will be the correct one. This will give you the correct result. Try to find it out. So I was just trying to mess with you guys. So Nikhil, very good. You found out the right one. So this is the one that is the correct one. So try to find it out. You will get the same constraint that you expect using this one. Okay.
Sir, before entering into all these conditions,
Uh,
the step where VC equals to VI into 1 by 1 plus j omega C C1 into RS plus R1 parallel R2,
uh-huh.
we take the bottom one, the denominator one,
Mm-hmm.
then if we are making it greater than 1, if j omega C1 RS plus R1 parallel R2 is greater than 1,
Yes.
then the VC1 will be automatically 0.
Yeah. True. 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 I'm not
We
denying
can,
that. I'm not
and I,
denying that. I'm just
yes, yes.
saying that should have come up with this expression also, right? I didn't do anything else. So what is the
Sir.
mistake that I made here? That I came up with this particular result. So this is not right, right? This is not correct. There is some mistake here. So I want you to find out that mistake. So in finding out that mistake, you will come up with three particular conditions, three types of conditions. So this one came up with this particular condition, right? You
Yes.
also have two more conditions. So if you try to find out the constraints on capacitor using these two conditions also, you will also get some different results. So which one is the most accurate according to you? Tell me. As a hint, I already told you that this one, the second one, will give you the most correct answer. Correct, the thing that you expect. So try to
The
solve this.
RD, the RD analysis was nice, sir.
What analysis?
RD. What should be the value of RD and how
Yeah,
why
yeah.
you should that was
Yes,
nice.
yes. So the same kind of thing you will also observe here. Okay. So these mistakes, why I tried to why I use why I used this condition was because I see a lot of students making this taking this assumption when we take quizzes here in IIT. Okay, in Kanpur. So a lot of students make these three kind of conditions are are the most common one among students, and that is why I went ahead and used these conditions here, because I want you to also involve in this. Try to solve this. Okay, the two conditions that I also mentioned here, try to come up with the expression, the constraint on C1 using these two conditions also use, and tell me in the next class what is the answer that you get. Okay, in the interest of time I'll just conclude here itself. I'll meet again on next Tuesday and I will ask you this one. I had nothing much to discuss, nothing else to discuss here. The swing limits and all, I think this was already covered, right? In the last session I think I covered swing limits, didn't I? Oh, I think I didn't cover swing limits. Okay, in the next session I will cover the swing limits also. Okay, I have not discussed any question on swing limits. I'll do that in the next session, surely. Okay, so for today I think this is it. We'll meet again on the next in the next class. There I will discuss more. Okay, and I'll ask you this. Fine.
Okay, thank you.
Thank you, sir. Thank you.
Thank you, sir.